Black holes, objects with a behemoth gravity force, distort space-time, sucking it in so quickly that not even light can escape. Well, where do the things entering a black hole go? The negative first law of physics states quantum information cannot be lost. This means that all information that goes into a black hole must stay in a black hole. Now we can define information as the bits required to tell us how to perfectly describe an object. For example, if you look at an orange, the information it is giving you is that it is round and orange. Physicists, however, are concerned with an object's quantum properties, or the properties of the particles making up the object, such as the particle's velocity, position, and spin. This information is measured in Plancks, the smallest fundamental unit capable of describing a particle's properties. Jacob Bekenstein found that the number of Plancks of information can fit into a black hole is proportional to the surface area of the black hole, not its volume. But then, along came a physicist named Stephen Hawking who discovered Hawking radiation, showing that over immensely long timescales, black holes evaporate. As the black hole evaporates, all the things that got sucked into the black hole are now gone as well. Now this appears as if information is getting lost, but that contradicts the negative first law of physics. So where does the information go then? This is called the black hole information paradox. In attempts to solve this paradox, Gerard de Hooft realized that the quantum information of an object entering the black hole could be imprinted onto the Hawking radiation before being radiated back into space. While waiting to be radiated back into space, the quantum information should be encoded onto the event horizon of the black hole. But how would the object experience falling in if its information gets encoded onto the black hole upon entry? De Hooft and Leonard Susskind figured that while the objects were falling into the black hole, that the object's quantum information would be encoded onto the black hole's 2D surface and would project a 3D hologram into its interior. But how can a 2D surface encode a 3D world? That's when string theory gets involved. Juan Maldacena, through the usage of strings, proved that space-time isn't flat, but instead has negative curvature. If you drew two parallel lines on a negatively curved surface, the lines would travel away from each other. We can stack our 3D universe on top of each other in different instances in time, creating a cylinder. Time being the fourth dimension, the cylinder's surface creates the fifth dimension. Information is being encoded onto this fifth dimension, projecting inward our familiar 3+1 dimensional world. Information that gets radiated by a black hole in the fifth dimension doesn't interfere with information in the lower dimensions we live in because the information radiated stays within the same dimension. Despite the different configurations, it's the same information projecting back into the lower dimensions we live in. This solves the black hole information paradox and hints at a holographic universe.